In the last video, we ended with a question about the neurotransmitter GABA, and the question was whether or not you think at physiological pH GABA would cross the blood-brain barrier. And we said that to cross the blood-brain barrier, we would need a structure that is primarily uncharged and hydrophobic. So we want to apply our acid-base chemistry here. So this is an amine, and this is a carboxylic acid. So carboxylic acid, if you remember from the first couple of videos, has a pKa of 1 to 5. And it is an unionized acid as drawn. And this amine is an aliphatic amine, not an aromatic amine, because we don't have any aromaticity. So this aliphatic amine, if you remember, has a pKa of 8 to 10. So this is review, but if you look at your amine, and let's focus on that. So for the amine, we're looking at an unionized base. And this unionized base, we are now going to compare the pH to the pKa. So we're talking about physiologic pH. So in this case, the pH of 7 is less than the pKa of 8 to 10. So we have an unionized base at a low pH, so it's at an acidic environment. Because it's in an acidic environment, it will be primarily protonated or in its ionized acid form. So you'll actually protonate this nitrogen and you'll have an NH3 plus with a positive charge. So that part is taken care of. We know it's primarily going to be in its ionized form. Now the carboxylic acid is AUA, pKa 1 to 5, so the pH is actually greater than the pKa. So we have an acid, the pH of 7 is greater than the pKa of 1 to 5. So we have an acid where that is put in a basic environment with a high pH. So an acid in a basic environment is going to be deprotonated. It's going to be in its ionized form. So it's going to be primarily in the IB form. And so it's going to be in the form where you get rid of that proton, that acidic proton, and you have your IB or your ionized negative form. So overall, the amine part is going to be positively charged, primarily ionized, and the carboxylic acid part is going to be primarily ionized with a negative charge. So this is clearly not an uncharged molecule. This is pretty charged, right? And you can apply this acid-base chemistry to any other structure and kind of determine, well, do I think this is going to cross the blood-brain barrier or not, based on my knowledge of needing uncharged hydrophobic compounds to cross the blood-brain barrier. So I'm determining, okay, we have a plus charge, we have a negative charge, it's very charged, it's hydrophilic, it's not hydrophobic, it will not cross the blood-brain barrier. Now the next question I want to go over is, which of the following structures do you think will cross the blood-brain barrier? And again, we have that same hint, a drug chemical structure will cross the blood-brain barrier if it is primarily in the uncharged or the unionized form and is hydrophobic. So again, it's not it is uncharged or it is charged based on this Henderson-Hasselbalch and pH versus pKa and all that we've been doing. It's all about percent unionized, percent ionized. So we need the majority to be unionized for it to more readily cross the blood-brain barrier. So take a look at these two structures if you want to pause the video and see if you think phenobarbital, or this structure down here, which is actually, I believe it's called barbaric acid. It's what phenobarbital is derived from. So looking at these two structures, which one do you think will more readily cross the blood-brain barrier and why? Okay. And so let's say again we're talking about a pH of 7. So I'm going to break this apart into the functional groups. So right here I see an amide, where I have a nitrogen sandwiched between two carbonyls. And right here I also have an imide. If you can't remember the pKa off the top of your head, just to review, the pKa of an imide is around 8 to 10. And it is in this top category of acids. So it's an acidic functional group, and so I know I have a UA, and I know that the pKa is around 8 to 10 for this imide. So imide, 8 to 10. So make sure you review those pKa's and have them memorized. So UA, imide, pKa of 8 to 10. And that's kind of the only acidic or basic functional group I see. Like this ring here is neutral, this alkyl group is neutral. So really I'm just dealing with an acidic functional group, a UA, at pH 7. So at pH 7, I have a UA where the pH of 7 is less than the pKa of 8 to 10. And so because the pH is less than the pKa of 8 to 10, then I'm going to say that this unionized acid, which is in a low pH or an acidic environment, is going to be primarily unionized. So do you think this would cross the blood-brain barrier? Yeah, I mean, if we're just thinking about acid-base chemistry here, we know that we have a UA, the pKa is 8 to 10, the pH is 7, the pH is less than the pKa, and so we are putting an acid in an acidic environment, and so it's going to be unionized. And the only way to have an ionized, to make your unionized acid ionized, you would have to put it in a basic environment. So you would actually want your pH to be greater than the pK. But in this case, we're putting an unionized acid in an acidic environment. The pH is low, so it's like an acid in an acidic environment. It's going to stay unionized. That goes back to the basic videos we watched earlier about acid-base chemistry. So that's phenobarbital. So I'm saying, okay, this is primarily unionized. So I think it's hydrophobic and it'll cross the blood-brain barrier. But let me just see what we're comparing it to. So again, I see my two familiar imide functional groups. I already determined in the last structure that these are imides. They are unionized acids, UA form, and we know based on the analysis we just did with pH versus pKa that these two functional groups will be primarily unionized at pH 7. But I also see something that's actually a lot more acidic. So having two hydrogens attached to a carbon, okay, right in between two carbonyls is actually very acidic. If you don't remember what this is a dicarbonyl group. So keep in mind that a dicarbonyl group is going to have, it is an unionized acid, it is one of the acidic functional groups, and its pK is more acidic than an imide. So its pK is lower, it's 1 to 5. So let's think about that. So we have a UA here. The pKa is 1 to 5. And so in this case, when we compare it to pH 7, the pH is actually greater than the pKa. So now we're putting an unionized acid or an acid into a basic environment where the pH is higher than the pKa. And so that means I'm actually going to have primarily my IB or my ionized form. Right? Putting an acid in a basic environment is going to ionize it or make it into primarily its IB form. So now, looking at this structure, I would say that I have a UA, so I have two UAs. Okay, I have a third UA, but these two functional groups are exactly the same in yellow, and these we determined are primarily unionized. But this more acidic dicarbonyl functional group with pK 1 to 5 is going to be primarily ionized. So comparing phenobarbital to this, where the structure that it originates from, which is barbaric acid, I believe that's what it's called, then I would see that phenobarbital is much more likely to cross the blood-brain barrier because it doesn't have that dicarbonyl. We actually have, instead of the 2 hydrogens you see in right here that are very acidic, pKa 1 to 5, instead we have CH2CH3, an alkyl group, which is neutral, and we have this aromatic ring, which is also neutral. And so when you're looking at these two, you're thinking, okay, so these two don't contribute to acidity or basicity, so they're just neutral. And that is exactly how phenobarbital is designed. So it was designed to substitute these two acidic protons right here, which make up that dicarbonyl acidic functional group. It was designed to get rid of those 2 acidic protons and replace them with an alkyl group and an aromatic ring, so it's less charged, right? So now, looking at phenobarbital, you don't have any primarily ionized form. You just have unionized form. So it will cross the blood-brain barrier, right? And so phenobarbital is actually a sedative hypnotic, and it's one of the oldest in its class of barbiturates. And because it is a sedative hypnotic, it does need to cross the blood-brain barrier. So that's why, coming from this structure that it's originating from, which is the second structure, that ionized part, right? That ionized part, that dicarbonyl, which is primarily in its ionized form, that had to be swapped out with something else. So that's why this phenobarbital, we would say, to answer the question, between phenobarbital and the second structure, phenobarbital will cross the blood-brain barrier. Okay, and this slide, or this picture here, summarizes your acidic functional groups, your neutral functional groups, and your basic functional groups. We also have 3 separate videos on acidic functional groups, neutral functional groups, and basic functional groups that you can review. Now would be a good time to pause the video and make sure you have these memorized. Make sure you know which functional group goes into which group, and then the pKa's that are shown here. You would want to know the carboxylic acid pKa. That's important. The phenol, the sulfonamide, the amide. Dicarbonyl could come up, so that one's good to memorize too. Aliphatic amine, aromatic amine. And then as far as pyridines go, make sure you know pyridine versus pyrrole. And know that the pyrrole is the one that's neutral and the pyridine is the one that's basic. And so make sure you can see the difference between the pyridine and the pyrrole functional groups. And yeah, and so this one, amidine and guanidine, this wasn't one of the pKa's that you would have to have memorized. So just focus on the highlighted ones over here. Okay, in the next video, we're going to go over clinical application questions to see if you can use your acid-base skills to save your patient.